Now we will discuss about the mathematical basics of grid convergence index, which is used to estimate the uncertainty in numerical simulation. So first, grid size. So we will start by defining this representative grid size H. For 3D problem, it is calculated using average cell volume, and for 2D problem, it is based on the total area and number of elements. So what is the purpose? The purpose is to convert the complex mesh into simple comparable parameter. So 3 grid size we can consider for different meshes. Fine grid we considered H1. Results will getting the phi 1. Medium grid H2, which gives the result phi 2, and coarse grid H3, which will give the result of phi 3. Phi 3, phi 1, phi 2 may be any parameter, velocity, temperature, whatever it is. So the purpose is to observe how the solution changes with the mesh refinement. So what is the grid refinement ratio? Indicated by R. R is a ratio of coarse mesh size and divided by fine mesh size. Okay, so H is a grid size. So coarse size divided by fine sizing of mesh. So it shows how much the mesh is refined between the grids. We are generally recommending this grid refinement ratio R is greater than 1.3, which ensures the valid comparison between the grid level. So next term is the order of accuracy, which indicates by P. It is calculated using P is equals to ln of phi 3 minus phi 2 divided by phi 2 minus phi 1 upon ln of R. So it tells us how fast numerical solution is converging. So what is the significance? Significance is if P is equals to 2, it defines the second order method. Higher the P, better the accuracy. So relative error E is defined by phi 2 minus phi 1 divided by phi 1. It means the difference between the medium and fine grid results. Significance is indicates whether the solution is stabilizing or not. Then the next term is a grid convergence index, GCI, which defines Fs into E divided by R to the power P minus 1, where Fs is a safety factor, which is usually 1.25. So CGI gives the percentage uncertainty in the solution. The significance are, if smaller CGI, reliable results will be there, and larger CGI need more fine mesh. So this method helps us to check whether our simulation results are independent of mesh sizing or not. Means if further increment in the mesh after fine mesh, there should not be any changes in the results. So it provides the quantitative representation or measures of error instead of just guessing the accuracy. So CGI is a standard validation tool used in the CFD and numerical analysis to ensure reliable and accurate results. So GCI quantifies how close a numerical solution is to the exact solution by measuring the mesh refinement uncertainty. I am repeating some terms which we used here. The first term is a grid size, which represents the mesh resolution. Smaller h means the finer mesh and usually more accurate results. So this term helps us to compare different meshes using the single parameter. Next term which we used in our PPT is phi 1, phi 2, phi 3. These are the results obtained from fine mesh, medium mesh and coarse mesh. They are important because GCI is based on how these values change with the mesh refinement. The next term is a grid refinement ratio R. These terms help us to understand how much the mesh is refined between the grids. The proper value of R greater than 1.3, as we discussed, ensures that comparison between the grids is meaningful and not too small. Next term we use, that is order of accuracy P. This indicates the rate at which the solution converges. It shows how quickly the error reduces when the mesh is refined. Higher P means better numerical performance of the method. Then next term is the relative error. We indicate with the E. This measures the difference between the two grid solutions, usually medium and fine. It tells us how much the results is still changing, which indicates whether the solution is stabilizing or not. And lastly, we use the term, that is safety factor Fs. This is used to add reliability to the uncertainty estimation. It ensures that the CGI value is conservative, not overly optimistic. And as we know, GCI, grid convergence index, which gives the percentage uncertainty in the numerical results. It is the most important output as it tells us how close our solution is to the exact or grid independent values. And based on that, we will take some numerical. So in this example, where we are talking about the work CFD variation example, it shows how to use results from 3 successively refined meshes to estimate whether the numerical solution is converging properly, what the order of convergence is, and how to close the finest grid CFD results is to the exact analytical answers. So we use laminar flow, pipe flow, where the exact center line velocity is 2.0 meter per second. The CFD values are 1.92 meter per second, 1.96 meter per second, and 1.98 meter per second on coarse mesh, medium mesh, and fine mesh respectively. So first, just we will be defining the mesh results which is given in the data. Fine mesh results, F1 I am taking phi1 or F1. In the discussion during the presentation of the topic, we have taken that phi1. So either you can take phi1 or F1. So fine mesh results F1 is equals to 1.98. Mid mesh results F2 is equals to 1.96 meter per second. Coarse mesh F3 or phi3 is equals to 1.92. And the grid refinement ratio, which we are assuming it is 2, that is R, right? So ratio of coarse mesh divided by fine mesh. So this means each mesh is assumed to be defined by the same factor. So the question is why we calculate the order of convergence that we discussed previously. So this order of convergence P tells us how fast the numerical error decreases as the mesh is refined. If the solution improves, it is predictable way, then the CFD model is behaving consistently. So now if we compute F3 minus F2 or phi3 minus phi2 is 0.04 minus 0.04, F2 minus F1 or phi2 minus phi1, that is minus 0.02. So in the magnitude point, the error reduced from 0.04 to 0.02. So which is the factor of 2, that is already hints at a first order convergence, right? So how to calculate the P now, which is a order of convergence? So P is equals to ln of F3 minus F2 divided by F2 minus F1 divided by ln of R, right? So in the discussion of previous PPT, we have taken this ln is equals to phi3 minus phi2 divided by phi2 minus phi1 divided by ln R. Now substituting these values, we will be getting the p is equals to 1. So this p is equals to 1 indicates the numerical solution is of first order convergence. That is the meaning of p. So if we are getting the p is equals to 2, then it is second order convergence. Now once we get the value of p, we will go for the Richardson extrapolation method, where we are trying to find out the exact numerical solution using the fine grid values, and the convergence behavior can be identified. So phi exact, that is a velocity exact value of velocity, or f exact is equals to f1 plus f1 minus f2 divided by r to the power p minus 1. So this value gives the exact solution, and that will be the output which gives the exact value of our velocity, may be equals to the free stream velocity. It should be the free stream velocity. So as per the calculations, we are getting f exact, which we are calculated with the help of Richardson extrapolation method. I am getting the value 2 meter per second. So the extrapolation values will be giving the exact value of our velocity, and which is matching with the solution. Now discretization error on the mesh refinement mesh, what is the percentage of error we can say, or relative error, what is the value of relative error? Value we have taken, that is 5 2 minus 5 1, that is correct. Will be equals to 0.02 meter per second. So relative error will be the difference divided by the actual velocity, that is 0.02 divided by 2 into 100, so 1%. So this states the discretization error on the finest mesh is 0.02 meter per second or 1 meter per second, 1%. So we can conclude that the verification quality is high for our case, because the solution improves as the mesh is refined, and the convergence trend is regular, we can observe. Richardson extrapolation gives the value of 2 meter per second, which is the exact value, and that agrees with the same analytical values. So this way we have to solve the numerical on such type of problems.